Welcome, everyone. I'm excited to kick off our presentation on organic chemistry. Today, we'll explore the fundamentals, key concepts, and fascinating reactions that define this essential branch of chemistry. We'll cover the basics, delve into important mechanisms, and look at real-world applications. Let's get started. Let's take a closer look at slide 2. Here, we're diving into the various aspects of organic compound analysis. Starting with quantitative analysis, this involves measuring the amount of each component in a mixture, which is crucial for understanding the composition and purity of compounds. Moving on, methods of purification are essential because they help us isolate specific compounds from complex mixtures, ensuring we can study them accurately. Then, we have hydrocarbons, which are fundamental organic compounds made entirely of carbon and hydrogen. They serve as the building blocks for more complex molecules. Structural representation is another key point. Being able to visualize and depict the structure of organic compounds is vital for understanding their properties and reactions. Next, qualitative analysis helps us identify what compounds are present in a sample, while functional groups are specific groups of atoms that determine how a compound behaves chemically. Classification of organic compounds ties everything together by organizing these compounds based on their structures and functional groups. Lastly, the introduction sets the stage for all these topics, emphasizing how these methods and concepts are interconnected in the study of organic chemistry. Each of these points builds toward a comprehensive understanding of organic compounds, which is the overall theme of this presentation. Welcome to this section on introductions. Here, I want to emphasize that making a strong introduction is crucial because it sets the tone for the entire presentation. It's your chance to connect with your audience right from the start. We'll cover key points such as clearly stating who you are, what you'll be talking about, and why it matters. These elements help establish credibility and spark interest. Remember, a good introduction isn't just about information. It's about engaging your audience and creating a sense of curiosity. Throughout this presentation, keep in mind that your introduction should seamlessly lead into the main content, making the overall flow smooth and compelling. Organic chemical compounds are all around us, appearing in everyday materials like clothing, fuels, polymers, dyes, and even medicines. These compounds are fascinating because, historically, people thought they could only be made by living organisms. But then, F. Wohler challenged that idea. He managed to synthesize an organic compound called urea from an inorganic compound, ammonium cyanate. This breakthrough was huge because it showed that organic compounds could be created artificially in the lab, blurring the lines between what was considered vital or life-dependent chemistry and inorganic chemistry. This discovery really opened the door to modern organic chemistry, allowing us to understand and create a vast array of materials that are essential in our daily lives. Let's take a closer look at the structural representation of organic compounds. When we talk about these structures, we're essentially visualizing how atoms are connected within a molecule. This helps us understand not just the composition, but also the shape and spatial arrangement of the molecule, which are crucial for its reactivity and properties. In organic chemistry, these representations allow us to see the backbone of the molecule, the carbon skeleton, and how different functional groups are attached. Recognizing these connections helps us predict how the compound might behave in different chemical reactions. By understanding the structure, we're better equipped to grasp the overall theme of organic chemistry, how the arrangement of atoms influences function and reactivity. So, structural representations are foundational. They serve as the blueprint for understanding the complex behavior of organic molecules. Let's take a closer look at some common hydrocarbons. Ethine, also known as acetylene with the formula C2H2, ethene or ethylene with the formula C2H4, and ethane with the formula C2H6. These are fundamental compounds in organic chemistry, and understanding their structures is key. When we talk about representing these structures, there are several methods. We have the Lewis structures, which are also called dot structures, where we show all the valence electrons as dots. Then there are dash structures, where we represent covalent bonds simply with dashes. Condensed structures group atoms together to simplify the view, and bond line formulas use lines to represent bonds, making the structure easier to interpret. Now, focusing on Lewis structures, we can simplify them further by representing two-electron covalent bonds with just a dash. This makes the structure cleaner and easier to understand, especially when dealing with larger molecules. Understanding these different structural representations is crucial because each provides unique insights. For example, Lewis structures help us see electron pairs, while bond line formulas offer a clear view of the molecule's backbone. In the context of this presentation, recognizing how these structures are drawn helps us grasp the bonding and reactivity of organic compounds. So, mastering these representations is a fundamental step toward understanding organic chemistry more broadly. Let's take a closer look at how we represent the three-dimensional structure of organic molecules on paper. The dashed wedge is used to show a bond projecting out of the plane of the paper and away from the observer. In contrast, the solid wedge indicates a bond that is projecting out of the plane of the paper towards the observer. By using these conventions, solid and dashed wedges, we can effectively translate a 3D image of a molecule into a two-dimensional drawing. This helps us visualize the spatial arrangement and understand the molecule's geometry, which is crucial for grasping its chemical behavior and interactions. So, these simple visual cues are key tools in organic chemistry for representing complex three-dimensional structures on a flat surface. Let's take a closer look at the classification of organic compounds. As you can see, organic compounds are categorized based on their structure and functional groups. This helps us understand their properties and how they behave in chemical reactions. We mainly divide them into several groups, such as hydrocarbons, which include alkanes, alkenes, and alkynes. These are the simplest forms, composed only of carbon and hydrogen. Beyond hydrocarbons, we have compounds with additional elements like oxygen, nitrogen, sulfur, and halogens. These groups include alcohols, acids, amines, and others, each with unique characteristics. Recognizing these classifications is essential because it provides a framework for understanding how different organic compounds interact and how they can be used in various applications. This classification ties back to our overall theme of understanding organic chemistry as a foundation for many fields, from medicine to materials science. These compounds are also called aliphatic compounds, and they mainly consist of straight or branched chain structures. When we talk about acyclic or open chain compounds, we're referring to molecules that do not form rings. Instead, their carbon atoms are connected in a chain that can be either straight or branched. This distinction is important because these structures form the basis of many organic compounds, including alkanes, alkenes, and alkynes. Understanding the nature of these open-chain compounds helps us grasp how organic molecules are built and how they behave chemically. So, as we continue, keep in mind that these acyclic compounds are fundamental to the study of organic chemistry, forming the backbone of countless compounds we encounter daily. All right, let's talk about alicyclic, or sometimes called aliphatic cyclic compounds. These are compounds where carbon atoms are joined together to form a ring structure, which is also known as homocyclic. Essentially, the carbon atoms are linked in a closed loop, creating a cyclic structure. Now, an important point to remember is that sometimes the ring isn't just made of carbon atoms. Other atoms, like nitrogen or oxygen, can also be part of the ring, and when this happens, we refer to these as heterocyclic compounds. So, to sum up, alicyclic or ring compounds are characterized by their cyclic carbon framework, and they may be either purely carbon-based or contain other elements within the ring. This structural feature influences their chemical properties and reactivity, which is why understanding these compounds is fundamental in organic chemistry. Aromatic compounds are a special class of chemical compounds that have unique stability and properties. You might be familiar with benzene, which is the classic example, but there are many other related ring compounds known as benzenoid compounds. These molecules feature a ring structure with alternating double bonds, which gives them their distinctive aromatic stability. This stability is due to a phenomenon called resonance, where the electrons are delocalized across the ring, making these compounds less reactive than other similar structures. Understanding aromatic compounds is key because they appear in many important chemicals, from pharmaceuticals to plastics. So, recognizing their structure and stability helps us grasp their role in chemistry and industry. Let's talk about hydrocarbons. These are organic compounds made up mainly of carbon and hydrogen atoms. They are fundamental because they serve as the primary components of fossil fuels like oil and natural gas. When we burn hydrocarbons, they release energy that powers our homes, vehicles, and industries. It's important to understand their structure and properties because they have a significant impact on both our energy consumption and environmental health. Hydrocarbons are also the starting point for many chemical products we use daily. Recognizing their role helps us better grasp the bigger picture of energy sources and their effects on our planet. Let's talk about hydrocarbons. These are compounds that contain only two elements, carbon and hydrogen. The key thing to remember here is that hydrocarbons are made up solely of these two elements, which makes them quite special in organic chemistry. They form the foundation for many important substances, including fuels like gasoline and natural gas. Understanding hydrocarbons helps us see how complex organic molecules are built from simple building blocks. So, whenever you come across a compound composed only of carbon and hydrogen, you can confidently identify it as a hydrocarbon. This concept ties into our overall theme of understanding organic compounds and their significance in everyday life. Let's talk about branched chain compounds. In these structures, small chains of carbon atoms are attached at one or more points along the main or parent chain. Think of it as a main road with little side streets branching off. These branches can vary in length and position, which makes each compound unique. When naming these hydrocarbons, we base the name on the overall chain structure. The suffix remains -ane because we're dealing with saturated hydrocarbons, but the prefix indicates the number of carbon atoms in the longest chain. This naming system helps us identify and distinguish different branched molecules. Connecting this to the broader picture, understanding the difference between straight and branched chains is essential because their structure influences their properties and how they behave in chemical reactions. Let's take a closer look at how to name branched alkyl groups. As we've discussed earlier, we follow specific procedures to assign the correct names. When there are multiple identical substituents, we use prefixes like di, tri, tetra, and so on, and separate their positions with commas. For example, if there are two methyl groups attached, we would say dimethyl and specify their positions accordingly. Now, if two substituents are attached at equivalent positions, we assign the lower number to the one that comes first alphabetically. This helps keep the naming consistent and clear. When different alkyl groups are present, we list them alphabetically, regardless of their position in the chain. Another key point is that we want to number the chain in a way that gives the branched carbon atoms the lowest possible numbers. This often involves choosing a numbering scheme that maximizes the numbers on the main chain's substituents. Finally, identifying the longest carbon chain in the molecule is essential because it forms the basis of the parent name. All these rules together help us systematically and accurately name branched chain alkanes, which is fundamental to understanding their structures and properties. Let's take a closer look at functional groups. These are specific groups of atoms within molecules that are responsible for the characteristic chemical reactions of those molecules. They essentially define the properties and reactivity of different organic compounds. Understanding functional groups is crucial because they help us predict how molecules will behave in various chemical reactions. For example, the presence of a hydroxyl group indicates that the compound is an alcohol, which affects both its physical properties and how it interacts with other substances. Throughout this presentation, we've seen how the structure of these groups influences the function of biological molecules, like proteins, lipids, and carbohydrates. Recognizing these groups allows us to understand the chemistry behind biological processes. So, in essence, functional groups are the key to unlocking the reactions and functions of organic molecules, tying everything back to the overall theme of understanding the chemistry of life. A functional group is an atom or a group of atoms that are bonded together in a specific way, and this is usually where the chemical reactivity happens in an organic molecule. For example, in molecules like CH3O, CH3CH2OH, and CH3,2-CHO, we see the O functional group. These compounds all have that hydroxyl group, and what's interesting is that they all tend to release hydrogen when they react with sodium metal. This reactivity is a key concept because it helps us understand how different molecules behave and interact in chemical reactions. Recognizing these functional groups is essential because they define the chemical properties and reactivity of organic compounds. Connecting this to the overall theme, understanding functional groups allows us to predict how molecules will react, which is fundamental in organic chemistry. Let's explore the methods of purification of organic compounds. When we talk about purification, we're aiming to remove impurities that can affect the compound's properties or reactivity. One common method is recrystallization, which involves dissolving your compound in a suitable solvent at high temperature, and then allowing it to cool so that pure crystals form. This method is especially effective for purifying solids. Another important technique is distillation, which is used mainly for liquids. By heating the mixture, the more volatile component vaporizes first, and then it's condensed back into liquid form, leaving impurities behind. There are variations like simple distillation for less complex mixtures and fractional distillation for more complex ones, where multiple components have close boiling points. We also have chromatography, which is incredibly versatile. It separates compounds based on their movement through a stationary phase under the influence of a mobile phase. Techniques like column chromatography or thin-layer chromatography help us isolate individual compounds from mixtures. Finally, solvent extraction is used to transfer a compound from one solvent to another, often to separate it from impurities. The choice of method depends on the nature of the compound and the impurities involved. All these techniques are vital tools in our organic chemistry toolkit. They help us obtain pure substances, which are essential for accurate analysis and further reactions. Connecting this to the overall theme, purification ensures the integrity and quality of our compounds, enabling reliable and reproducible results in our work. Once an organic compound has been extracted from a natural source or synthesized in the laboratory, the next crucial step is purification. This step is essential because the compound we want is often mixed with impurities that can affect its properties and applications. The methods we choose for purification depend on the specific nature of the compound, as well as the type of impurities present. Different methods are tailored to separate compounds based on their physical and chemical properties. For example, some techniques exploit differences in boiling points, while others rely on solubility or polarity. Understanding these properties allows us to select the most effective purification method. This is a key concept because, in organic chemistry, purity is often vital for further reactions or analysis. So, mastering these purification methods ensures that we obtain a pure, reliable compound, which is ultimately essential for research, industry, and application purposes. Now, let's look at some common techniques used for purification. First, distillation. This method is primarily used to separate volatile liquids from non-volatile impurities, especially when the liquids have sufficiently different boiling points. It works because each component boils at a specific temperature, allowing us to separate them based on their boiling characteristics. Next, we have crystallization. This technique involves taking a solution and allowing the pure solid to form crystals as it cools or evaporates. An important point here is that during crystallization, the solid directly changes from a solid to a vapor form without passing through the liquid state. This process is very effective in obtaining pure solids from mixtures. Finally, sublimation. Sublimation is a fascinating process where a solid turns directly into vapor without melting into a liquid first. This is especially useful for purifying substances that sublime, as the impurities that do not sublime are left behind. All these techniques, distillation, crystallization, and sublimation, are key tools in our laboratory arsenal, helping us isolate and purify compounds efficiently in line with our overall goal of obtaining pure substances. Let's delve into the qualitative analysis of organic compounds. This slide highlights the key methods we use to identify what organic compounds are present in a sample without focusing on their quantities. The main goal here is to understand the composition based on observable properties and reactions. Qualitative analysis typically involves a series of tests that detect specific functional groups or elements within the molecules. For example, we might use simple chemical reactions, such as adding reagents that produce a color change or a precipitate, to identify certain groups like alcohols, aldehydes, or carboxylic acids. Another important aspect is the use of instrumental techniques, like infrared spectroscopy, which helps us identify characteristic bonds and functional groups by their unique absorption patterns. These methods are essential because they provide a quick and reliable way to analyze complex mixtures. Connecting this to the overall theme, qualitative analysis is fundamental in organic chemistry because it helps us understand the structure and reactivity of compounds, which is crucial for synthesis, quality control, and research. It's all about recognizing and understanding the molecules' identities, setting the stage for more detailed quantitative analysis or further chemical reactions. When we talk about organic compounds, the main elements you'll find are carbon and hydrogen. These two are the backbone of most organic molecules. However, organic compounds can also contain other elements that add to their complexity and functionality. These include oxygen, nitrogen, sulfur, halogens like fluorine, chlorine, bromine, and iodine, and even phosphorus. Recognizing which elements are present helps us understand the properties and reactivity of these compounds. Remember, the diversity of elements in organic chemistry is what makes it so fascinating and essential in fields like biochemistry, medicine, and materials science. So, the key takeaway here is that while carbon and hydrogen are fundamental, the presence of additional elements broadens the scope of organic chemistry significantly. Now let's look at how we can detect the presence of carbon and hydrogen in a compound. When we convert hydrogen to water, we can test for it using anhydrous copper sulfate. When it reacts with water, the copper sulfate turns blue, confirming hydrogen's presence. Similarly, carbon, when oxidized, forms carbon dioxide, which we can detect by bubbling it through lime water. If it turns cloudy or develops turbidity, that indicates carbon dioxide is present. To specifically detect carbon and hydrogen, we heat the compound with copper, Roman II oxide. This process helps us identify these elements based on their reactions, and it ties into the larger theme of analyzing compounds through chemical reactions. Understanding these detection methods is fundamental in confirming the composition of organic substances. Let's walk through the process of testing for phosphorus first. The compound is heated with an oxidizing agent, which in this case is sodium peroxide. After that, the solution is boiled with nitric acid, and then we add ammonium molybdate. If phosphorus is present, this reaction produces a yellow color or a precipitate, serving as an indicator. Moving on to halogens, the test involves treating the sodium fusion extract with nitric acid to acidify it, and then adding silver nitrate. The type of precipitate formed tells us which halogen is present. A white precipitate indicates chlorine, a yellowish precipitate suggests bromine, and a yellow precipitate points to iodine. Next, for sulfur detection, we again start with the sodium fusion extract, acidify it with acetic acid, and then add lead acetate. The formation of a black precipitate, which is lead sulfide, confirms sulfur's presence. For nitrogen, the process involves boiling the sodium fusion extract with iron, Roman II sulfate, followed by acidification with concentrated sulfuric acid. If nitrogen is present, This reaction results in the formation of a Prussian blue color, which is a clear visual confirmation. Finally, for other elements that might be present in an organic compound, we use what's called the Lassane's test. It's a general test that helps us detect various elements beyond the main ones we've discussed. These tests are crucial because they help us identify the elements present in organic compounds, which is essential for understanding their structure and properties. Now, let's turn to slide 25, which focuses on quantitative analysis. Here, we're emphasizing the importance of using numerical data to support our findings. Quantitative analysis allows us to measure and compare key variables objectively, giving us clearer insights into the trends and patterns within our data. It's crucial because it provides a solid foundation for decision-making, ensuring our conclusions are backed by concrete evidence. Throughout this presentation, we've been discussing various strategies and insights, and this slide reminds us that integrating quantitative data strengthens our overall approach. It helps us move from assumptions to evidence, making our recommendations more credible and impactful. So, as we continue, keep in mind how vital these numbers are in shaping a comprehensive understanding of the subject at hand. Now, as a result of the combustion, carbon dioxide and water are produced. The water isn't just any water, though. We determine its mass using anhydrous calcium chloride, which is great at absorbing moisture. This helps us measure the water produced accurately. To find out the amounts of carbon and hydrogen in our organic compound, we start with a known mass of it. We burn it in an excess of oxygen and copper, Roman II oxide. This ensures complete combustion, so all the carbon turns into carbon dioxide and all the hydrogen turns into water. By analyzing the amounts of carbon dioxide and water formed, we can work backwards to determine the original amounts of carbon and hydrogen in the compound. This method is fundamental for understanding the composition of organic substances and ties directly into our overall goal of analyzing chemical composition through combustion. Now, moving on to how we actually quantify nitrogen in these compounds. One common approach involves heating the compound with concentrated sulfuric acid. This process converts the nitrogen into ammonium sulfate. The key is that the ammonia released during this process is then captured by absorbing it in an excess of standard sulfuric acid solution. This method helps us accurately measure the nitrogen content by converting it into a measurable form. Next, let's talk about Kjeldahl's method. In this technique, the nitrogen-containing organic compound is heated with copper oxide. This reaction releases free nitrogen gas, which we can collect and measure. And then we have the Dumas method. There are two main approaches here for estimating nitrogen, but both involve combusting the sample at high temperatures to convert nitrogen into a measurable form, usually nitrogen gas, which is then quantified. These methods are fundamental because they allow us to determine the nitrogen content accurately, which is crucial for assessing the composition and quality of the compounds we're working with.